Uh, Welcome back. We are now going to solve a discrete time Fourier transform problem. And the question is as follows. Let x of n be equal to 1 plus cosine 2 pi over 4n and let y of n be equal to sin 2 pi over 4n. We're in this problem we're asked to calculate y hat of k, which is the discrete time Fourier series coefficients, and with this to calculate the convolution of x star y of n. Okay, first we're going to calculate x of n as follows, which we're going to calculate following function. It's discrete time Fourier series coefficients. We're going to use the following formula to do so. This is the formula for obtaining the discrete time Fourier series coefficients for the following function, like that. And this notation over here just means any consecutive capital N integers that we're going to summate. And then over n, kn. So this is just our formula for the discrete time Fourier series coefficients of this function right here. Okay, but there's an easier way. We're going to use Euler's formula. And it will break this into its components, which we call Euler's formula. Is something like this: 2 pi over 4 n I plus e to the negative 2 pi over 4 n I, like that, which will give us 1 plus a half e to the pi over 2 simplifying, plus 1/2 e to the negative pi over 2 n I. Okay. And now it is apparent that using Euler's formula that the coefficients are as follows. So obviously, looking back at the formula for calculating the discrete time Fourier series coefficients, that to obtain a 1, the only way possible is for this complex exponential term to have a 0 in the exponent. So the only way possible is if, obviously, that k is equal to 0, which will give us our f of n. So at k equals 0, we'll have the following complex Fourier series coefficient. At 0, k equals 0, recall like that, which will give us, obviously, a 1. So, this should be an x. I beg your pardon. Just for notation's sake. And on this term, clearly, pi over 2 and I, the k from the formula would have to be, this should be 4, so plugging in for the values we know, n is equal to 4. Why is n equal to 4? So if we look at the fundamental period of this function x of n, we'll see that omega is equal to 2 pi over 4, which is equal to 2 pi over t, and t is equal to 4, which is an integer, so that is the fundamental discrete period of the function x of n. So knowing this, we'll just plug it into our formula for capital N, and we will obtain that. And back to our complex exponential term here we got from Euler's formula. So clearly, for these, for the formula to get this complex exponential, we have to have a k which is equal to -1, basically. So with a k of -1, we'll obtain the complex Fourier, discrete time Fourier coefficients would be a half, as you can see, obviously. And similarly, this complex exponential is just a negative of this complex exponential. Thus, it can be concluded that k is just 1. And similarly, this is the discrete time Fourier series coefficients. So then, knowing these three discrete time Fourier series coefficients, we can conclude that for all k which is not equal to plus or minus 1, hold on here, we need a little bit more space, plus minus 1 mod n, which is in this case 4, or 0 mod 4, for all k which is not plus or minus 1 mod 4 or 0 mod 4, the complex Fourier series discrete time coefficients will be 0. Thus, we can conclude in general terms that our discrete time Fourier series coefficients is equal to 1 if k is 0 mod 4, a half if k is equal to plus or minus 1 mod 4, and 0 for all other k. Okay, so that's the complex Fourier series coefficients of x. Now let's do the complex. Oh man, we're running out of time here, so I'm probably going to have to split this into 2 videos, so we're going to go really, really fast with the second part. Y of n. Okay, so we're going to write down y of n is equal to sin 2 pi over 4n. Okay, so we know similarly here that the fundamental period of this function with respect to discrete time will be 4 as well. You can check that yourselves, but I'm running out of time in this video, so we're just going to go through with it, and we're going to see that similarly that the formula for calculating complex exponential terms is equal to 1 over 4 summation n4. This is going to be 4x of n e to the negative 2 pi over 4 k n. Okay, that's going to be our formula here. And 30 seconds left. I don't know if I'm going to finish on time, so we're going to use Euler's formula again, but this time we're going to have Euler's formula. So we're going to have e to the 2 pi 4 and I minus e, and we're going to have a complex number here because it's a sign, and you should know that by now, and then negative 2 pi over 4 and I. So we're going to expand this out, and we're going to get 1 over 2 pi So we're going to get this minus 1 over 2I e to the negative 2 pi over 4ni. We're going to get that. Okay, and then it's 10 seconds, and I'm going to make another video, and I'm going to explain the rest of it later. Thank you for watching, and stay tuned.